learning to communicate and correct pose errors. Learned communication makes multi-agent systems more effective by leveraging distributed information and computation. However, relying on distributed information makes individual agents susceptible to erroneous messages. In our work, we study V2VNet, a state-of-the-art collaborative self-driving network. We illustrate the setting in this figure. We show a simplified case where the ego self-driving vehicle, in red, receives a message from one other self-driving vehicle, in blue. Both self-driving vehicles use a convolutional neural network to process the input LiDAR to produce a spatial feature map, called the message. To use the incoming message, the ego must warp the spatial feature map to match its own perspective. We can see with a well-aligned message, the ego gains considerable visibility into the scene. However, with pose noise, the warping is not successful and results in unusable features. Once warped, the incoming messages are aggregated using a graph neural network, detailed in the V2VNet paper. The aggregated messages are then used by the network to perform detection and motion forecasting, which we call perception and prediction, or P&P. Realistic pose noise has been shown to diminish any gains over solo vehicle P&P. We propose a method to resolve this issue. Our method is an end-to-end learned neural reasoning framework. This system corrects incoming messages before they are aggregated by V2VNet's graph neural network. We will focus on the ego in this figure. First, we use a pose regression module, which uses the ego's message and a warped incoming message to predict the relative error between the ego and the other. This is done for every incoming feature map. Next, to refine the relative pose estimates, we use a consistency module. This allows vehicles to communicate corrected relative poses to reach a consensus about each other's pose. We achieve this via a robust probabilistic transformation synchronization algorithm. Concretely, we use a conditional Markov random field where each vehicle's pose is a node, and we condition on the predicted relative poses. After the vehicles reach a consensus about poses, there may still be outliers poisoning the messages. Given a refined, warped message and the ego message, we predict an attention weight for the incoming message. This is used in a weighted average during the graph neural network aggregation in V2VNet. Finally, these corrected messages are then used in V2VNet to perform P&P, perception and prediction. We are primarily interested in the P&P performance of our model under significant pose noise. We compare our method to the original V2VNet, V2VNet with data augmentation, and Learn to Sync, another state-of-the-art synchronization algorithm. With our proposed method, we see nearly constant perception and prediction performance for noise seen in the training set. In the training set, we use 0.4 meters and 4 degrees standard deviation of noise. We still see reliable performance of our model for noise not seen in the training set. We also evaluate the performance of our relative pose correction. Our method shows significant reductions in both root mean squared error and mean absolute error for both positional and rotational noises. This implies that outliers in the predictions don't poison all of our consistent pose estimates, unlike for other methods. To conclude, collaborative self-driving will bring the safety of self-driving to the next level. In order to be safe in realistic conditions, we must be robust to noise. We propose and empirically show the effectiveness of an end-to-end learned neural reasoning framework, where vehicles correct errors, reach a consensus about those errors, and suppress remaining outliers. In the future, we aim to extend our framework to correct more general types of noise. Thank you for listening.